Hi, welcome to the first in the Pangolin video series. As a brief introduction, a number of other firmware that I write, such as H4 and H4 plugins, are all asynchronous. And they started out by using the excellent PubSubClient library, but it's not asynchronous, and for various reasons I didn't want to use it. It's quite limited and only works at QoS Scearo. So I hunted around for a library that would run MQTT asynchronously, and I came across asynMqttClient. And I looked at it, and I looked at the claims, and I made a very bad decision, which cost me a lot of time, a lot of pain, a lot of grief. And that decision was to use that library because I believed what it said it could do. Most of what it said it can do isn't correct. It's highly unstable, it crashes all the time, and it's full of bugs. And the rest of this presentation will go into that in detail and show you why. But it was so bad that I decided that I had to write my own version because there was nothing else available at the time. And that's how Pangolin was born. So read on. But first, please subscribe to the channel, click on the like button, click the bell icon to get notified, and support me on Patreon if you can. There's a link in the description below. These main features of the asynMqttClient library from its GitHub page. Now, from this point forward, I'm just going to say the library or this library because it's a bit of a mouthful to say. There are other libraries I'm going to mention. I'll mention them fully by name because they only come up once or twice. But for this library, we're going to look at these features and we're going to examine them in detail, one at a time. And we're going to look at the features in red, and I'm going to discuss why these are not correct, why the library fails in a number of areas, and give you the evidence of these red statements. So first of all, it says it's 3.3.1 compliant. It absolutely is not. It breaches the protocol in numerous ways, and that's not just a technical problem. It's a functional problem because the MQTT 3.1.1 protocol defines QoS, quality of service, sessions and recovery, and because it doesn't fully comply with the 3.1.1, it doesn't fully comply with QoS 1 and 2. More detail later, but the point is it is absolutely not compliant. It claims to be fully asynchronous, and it can be partially forgiven for this because it relies on an underlying library called ESP async TCP, and that library itself has a major bug to do with being used fully asynchronously. Subscribe and publish at QoS 0.1 and 2 is totally and utterly untrue, incorrect and wrong. It functions only at QoS 0, and even then it doesn't do that very well. That's only partially true, but again, this library can't be blamed too much for it because on an ESP8266 the TLS options are extremely limited. So that's a direct reflection of the state of TLS support. Whether or not it's available in the platform IO registry is a matter of greatest indifference to me. What matters more is what isn't shown there, and I shall continue in red. It has a bizarre, illogical and incorrect API, some of which prevents it from being able to comply with 3.1.1. It experiences frequent random disconnections and reconnections. The GitHub issues page is full of dozens and dozens and dozens of people complaining about this, and they have been for 5 years. And since that was about the last time it was updated, they're going to be continuing to complain for a long time to come. It experiences frequent random crashes. Same again in the issues page. It can't handle large packets. It can't handle publishing things rapidly, which is related in part to the fully asynchronous and the ESP async TCP bug, and it behaves differently depending on how it's built, which is at the user discretion over which the library has no control. And when I say behaves, I mean it crashes differently depending on how you build it. So finding these bugs took me quite a while, and I found it and catalogued at least 16 of them, all of which prevent it from being used in any of the ways that are claimed here. So let's move on in detail. We're going to go for a caveat, we're going to look at the problem, and then we're going to look at the evidence, and then there'll be a summary. So the caveat is that this has been made on the 5th of June 2021. You can see there that it's mostly 4 and 5 years ago that the major changes have been made to the library, so I'm pretty sure that everything I'm about to say still holds true. There have been some recent changes 12 days ago, but I took a brief look and they're very, very small, and I would stake money on the fact that they make no difference whatsoever to substantive problems that exist. So let's move on. So here's part one. If everything I've said is true, which it is, and I shall prove it with the evidence, why on earth would anybody use it? I'm going to look at some unarguable facts, some basic facets of the C language and programming in general, which are not up for dispute or discussion. And we'll then look at how they combine together to provide what I call the perfect storm, which is the fundamental flaw in this library which prevents it from being able to work and prevents it from actually being able to be fixed without being totally rewritten. So why would anyone use it? Well, because most folk only use QoS 0. So who cares about 1 and 2, where a lot of the problems lie? Most folks send only small packets of data, a few bytes, like a temperature here, a humidity there, once a minute. Small packets aren't a problem. Sending them at a slow rate isn't a problem. And most people aren't sitting there with an analytical eye and diagnostic software in place watching Wireshark monitors for disconnections and reconnections, so they just don't spot them. All that happens is that data gets lost. Data gets thrown away, messages get lost, but if you're only checking your temperature twice a day, you don't see that it failed to update 50 times. So that's why anyone would use it, because they use a very small portion of it that happens to coincidentally work, and you'll see why I said that as we go on, because it only works at all by chance in that very small subset. If you go outside of those parameters, it fails instantly. So most folk think it works, but anybody stepping off that happy path immediately sees that it's totally unfit for purpose. So to those people who think it works, I can assure you it does not, because it does it only by chance, and the chance sometimes doesn't pay off, and then it crashes and fails and reboots. Again, if you're not looking, you don't spot that. But the flaws are so bad and so many that it didn't take me long to realise that it was irrecoverable, and therefore my only course of action was to write my own library, which I then did. It's called Pangolin. There's the link will be in the description. It not only corrects all of the errors that are found in this library, but it adds a whole lot more functionality too. These are the facts then. Now the first two will be known by anybody who's ever done any C++ programming for more than about a week, because they're things that even the most junior and inexperienced of programmers will know. And the first is what we're going to call the dangling pointer. And this says that if you create or allocate a memory pointer, once you've deallocated, you must not use it again. It is no longer valid. It does not point to valid memory. And on most MCUs, any attempt to even just read what it points to will result in an invalid read, hardware exception, and a crash. local variable scope is probably even more basic. If you declare a local variable in a function, when the function exits, that local variable ceases to exist. So if you add up 1 and 2 and the local variable contains a pointer to some memory, you try to access it. Once that function has exited, it's going to crash. And finally, there's a problem from asynchronous code. Now, again, there's perhaps partial mitigation because this is an advanced and notoriously misunderstood concept. However, the library sets out to be an async library. It claims to be fully asynchronous. You'd wish and hope that the author understood how to program asynchronously, but as you will see shortly, he obviously does not. Because if you call a function into asynchronous code, you have no control whatsoever over when it completes. That's pretty much what asynchronous means. You request a feature, and when that feature is ready, sometime in the future, you will receive a notification that it's complete. If you continue having started that process without waiting for that notification, or even blindly without even checking it, and what you do depends on the fact that it has finished when it might not have even started, then you are certain, almost certain, to fail at some point. And because it depends on timing, that can often appear random. So the one thing you would not want to do would be to create a memory pointer in a function, pass it to an asynchronous function, exit your own function, thereby destroying the pointer, and then immediately start using it without ever having anything in place to check the asynchronous return at some unspecified future point. Because knowing what you know now, that would be a route to disaster, wouldn't it? Well, that is exactly what this library does on every single call to the asynTCP API. And it's that type of thing that leads me to believe that the author really didn't understand what he was doing, which doesn't give me much confidence in the rest of the library. And I think if you understand what happens over the rest of this presentation, you'll agree with me. However, let's stick to the facts. So we now have a situation, as what I'm calling it the perfect storm, where we've got a fundamentally flawed code calling a fundamentally flawed async TCP library and then not checking the return result or scheduling itself correctly to receive the notification, which then call a highly configurable, and that's the key point here, TCP provider library called LWIP. So the final fragile plate on top of the wobbly stack is that the default ESP8266 implementation of LWIP is configured with the default option of telling LWIP never to copy any pointer that it is passed. Because the only mitigation to the previous scenario would be if the library you passed it to and then immediately invalidated the pointer. If that had made its own copy of it, then it wouldn't need to reference the pointer anymore and the problem would instantly go away. However, that is not the way that LWIP is delivered. So that's why it's a perfect storm, because you could not have designed it any better way to always fail. Hold on a minute there, Phil. Always? Yes, always. The only times when it works are by chance, and I'm going to show you that in very careful detail as what follows. Now then, I'm going to switch to my big fat pointer for this one. Be with you in a second. Here we have a timeline going downwards. It starts with a user calling this library saying, hey, send this data for me. And at the far end of this ripple down chain, we have the network which receives the data. Don't forget also that the MQTT is a bidirectional protocol, so that network is randomly out of the blue going to receive data as well and wake you up and send you some. So we've got transmit, TX for short, and RX, receive issues. This is just looking at the transmit issues at the moment. So the sequence of events is this. That the user calls a library, and the library inside a function creates a local variable, and that local pointer, I'm calling it LP for short, that LP is passed to ESP async TCP. That library in this scenario just really acts as a middleman between this library and LWIP. Really doesn't do a huge lot more than kind of just forward it. But it provides a much simpler interface because LWIP is a particularly complicated beast. So for the rest of this, ESP, you could kind of factor it out, but I didn't want to do that. I wanted to give you the full exact picture, but yes, you kind of got a straight line through it. So the local pointer is passed to LWIP. Now this is where it starts to get interesting, and this is where asynchronous programming comes in, because LWIP puts that request in a queue stroke buffer, and having done so, immediately returns to the caller. There is absolutely no guarantee at that point that any data has been sent, that the network has even been spoken to. That's what async means. You call that to send, diddly diddly diddly, it gets queued, and then we come back. The data does not get sent until sometime in the future. You have no control over what time that is. You don't know when it's happened, and if you refuse to listen to the message about when it has happened, you are in deep doo-doo. So far with me? So, the message is queued at this point in time, and the return is controlled to the middleman, which just basically shunts it on up back to the caller. The caller then returns to the user code, and as it returns to the user code, it destroys that local pointer. Now this line here between what I'm calling the lucky zone and the danger zone is where the problems occur, because if that pointer is accessed any time after that point in time, it will almost certainly fail, because this invalidates it. It is deleted and no longer exists at that point, or the data that it points to, let's say. So, if when the network decides it wants to do a sending is any time after that, then we have the perfect storm, because anything that accesses the pointer has got a serious problem. Is that there's no guarantee that the data is valid, still there, or even that the pointer currently points to a valid address. Because if the user code has reallocated that pointer to something that's useful, then accessing it is going to be a problem. However, let's move on. If by chance the network has done the send and sent the acknowledgement, known as an ACK, by about here, you're in the lucky zone, because at the point it did that, that pointer was still valid, and everybody was happy. But that's a very, very slim window. That's a very slim window. And this second scenario is by far the much more common. Now then, that timing window between luck and danger is affected by an immense number of variables, which make it almost impossible to predict what's going to happen here. One of the things that affects it is the bug in the ESP async TCP library, because the cherry on the top is that that bug tends to extend that danger zone, and I'll show you why. So this is what I'm calling the overlap bug. and I need my big pointer again. We transmit 10 bytes. The network sends them and sends us an acknowledgement or an ACK for 10 bytes. So it's like ping pong. Send ACK, send ACK, send ACK. And in this ping pong scenario, where you get acknowledged for how many bytes you've sent every time, ping pong, ping pong, ping pong, everything works. Everything works fine when that happens. But this is a fully asynchronous library, isn't it? And what that means is you don't have to wait for that ACK before doing your next send. You can go send, send, send. And what you should get back is ACK, ACK, ACK. But it's perfectly valid to get send, 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 big fat ACK. So you could do 3 separate sends of 10 and then get a single ACK of 30 back because of the way that TCP works, because TCP at the LWIP level can pack those multiple sends into a buffer, single buffer, if they occur in rapid succession, to save overhead on the network and only send 1 packet instead of 3, because every packet's got a time overhead. So, okay so far. The bug is that if you do this, if you overlap those transmits, if the TXs overlap each other without the appropriate intervening ACK, TX ACK, TX ACK, TX ACK, without the ping pong, it fails. There's a bug in it. Now there's, I think, 4 valid responses to that TX sequence. One of them is ACK 10, ACK 10, ACK 10. Another one is ACK 30. Right? Another one would be ACK 20 followed by an ACK 10 because it packed the first 2 into a single buffer and then sent the separate 10. Conversely, an ACK 10 and an ACK 20 coming back in would both keep the picture in sync. The bug is this, that during the overlap it miscalculates the number of acknowledged bytes, and it does it in such a way that it might give you 1 ACK 10. So any other code thinks, well, I've still got 2 outstanding TX10s waiting to be ACKed, so I'll hold them to those buffers until I get those ACKs. The problem is those ACKs are never coming. So ESP, TCP, gradually starts leaking memory and eating up memory. And the rate at which it does that, of course, is dependent on the size of that window, the size of that. It's dependent on a lot of things we're going to cover in a minute, which is what makes the outcome unpredictable and appear random. Because sometimes you might get that first ACK, the first combined ACK for 20, or you could get 2 ACKs of 10. What you will never get is the 3 ACKs or the 30 ACK or those other 2 valid ones. The overlap bug is that if you overlap sends, the ACK response will be incorrect in one of several ways. It's quite a complex little thing, but that's the point. And that brings us to probably the most beautiful irony of all, in that, you remember back to that claim earlier on the front page, where it says it's fully asynchronous. The only part of that that's true is that it calls a library which calls a fully asynchronous library, because it only works if you use it synchronously. If you actually use it asynchronously by sending multiple overlapping sends, it will fail. It will fail. This is not Phil's opinion, or sometimes it will fail. And that depends on the rate at which you send them. So if you send them slowly, you never see it. If you send them quickly, you see it every time. You lose data, you get random crashes, you get heap exhaustion bugs. It will fail. And there's why. A lot of people are unhappy with this term undefined behaviour. Well, what does that mean? Well, I don't know. It's undefined. That's the whole point. Why is it undefined? Because here's the possible outcomes. Critical factor is when that ACK network ready, when that ACK comes back within the window of the lucky zone. If it does, then most folk will see their apps working. They'll wonder what all the fuss is about. Most of them, to be fair, won't even understand half of what I've said so far. However, if it comes back in the red zone, pretty much anything could happen, because if by pure chance the original data is still where it was when the pointer to it was deleted, then it'll be like nothing's happened and everything would appear well. It did not particularly well, because there's plenty of other bugs which we'll cover in a minute. But do you get the point? It's only if that pointer has been reused by the calling user code, over which this library has no control whatsoever, therefore you can't predict what will happen. Only if that coincidentally still points to where it used to will it work. And that is pure chance. And that's why I say it absolutely does not work, never works, and never can. It just coincidentally happens to look like it is reasonable enough portion of the time so that most people think it's okay. Because if the calling program isn't actually doing much and it isn't shunting much memory around, then the likelihood of that memory being reused is low and the data will still be there. But that's the really lucky zone. So let's just look at some of the other factors. There's a thing, I've talked about the amount of data being sent. I've talked about the rate at which it's sent. If you multiply the two together, you get a mythical feature called load. It's the kind of bulk amount of data that's being sent at any one time. It's like bandwidth. So it's D for the amount of data and S for the rate at which it's sent, combined together, need to be less than the rate at which ESP82 async TCP and LWIP can clear that data from their buffers to the net. And that relies upon them correctly acknowledging what's been sent and what's come back, which we know we won't do if the rate is high. You see where the first problem comes. So even if we could calculate these things, the code is so broken it would make the answer always wrong anyway. But the point is this: if the load, which is the amount of data and the rate at which we sent it, divided by the rate at which it can be cleared is greater than 1, then it means you're sending it too fast and things start to back up and bottle up, even if they were all properly controlled. So unless you reduce that rate, or at a certain point start ignoring any data that's sent, then you're going to get a problem and a crash. And that process of doing that is known as flow control. And this library has none. It has no flow control in it whatsoever, because it relies on, I'm going to have to wind back for this, it relies on that happening. Short send, quick reply, short send, quick reply, short send, quick reply. So little data sent so rapidly, slowly, that it fits in that window and you actually get a reply back before you exit that function. And when that's the case, it seems to work. So even if it did have flow control for the times when it didn't work, we would have what I call the Donald Rumsfeld problem, which is that there are unknown unknowns. Now I'm going to classify the values that we're going to talk about into 3 separate categories. There's one where things are completely unknown and are beyond our control, and they're the Rumsfeld ones. They're the unknown unknown. Well, actually, no, they're the known unknowns. Example is network latency. There's no way the code can tell how good your network is and how quickly it can send and receive packages. You just can't calculate it. So the only thing you can do with figures like that, which hugely affect the way your program works, is to put in code that mitigates the problem. Explain that in a minute. Those are what I call the don't knows. Right? Then there are values that are discoverable, but this library makes no attempt to discover them. So they are what I call the don't cares. Then there's a subset of those values for which instead of actually trying to find out what it is, you just kind of say, well, I'm just going to guess. I'm going to make a figure, you know. Right. Now then, here is an analysis of this library and the variables that affect the difference between the green zone and the red zone, and the timing, and whether you're lucky, really lucky, or you hit the danger zone and crash. Now, look, we're getting nearly half an hour already. I don't want to go through these in too much detail, but basically, structure of the user code, it doesn't depend on anything. It doesn't depend on any other variable. Its class is don't know. The sending load depends on data rate, data size, and the clearance rate. Clearance rate depends on the buffer size, network quality, and the RF quality. Right, so take any one of these, and at the bottom of its chain, there's a figure that you don't know. So if you don't know one of the component figures, you can't possibly know that figure. So almost every figure that affects this problem we're talking about falls into the Rumsfeld category of you don't know what it is. There's only two figures on there that you do know and can find out, and in this library they both fall into the don't care category because they're not even checked. They're never even looked at. So just by knowing that in the code, you know that this cannot handle, cannot properly manage asynchronous communications. Now, its biggest sin, however, is this. That obviously you can't know the received data size. MQTT, you listen to a topic, and if you've got a buffer that can hold 1K and somebody sends you a 10K message, you're in trouble because it won't fit in the buffer. So unless you have code in place to mitigate that, you're going to crash. So, or you're going to lose 9K of data. Either way, the point is made, is that you have to be able to know and manage unpredictable data that could be sent to you. And the only way that you can do that, the only way, is by knowing the size of the buffer that it's coming into. Well, we've already said that this lib never checks or calculates what that size is. So you already know most of what I'm going to tell you. What you don't know the implications of it, but you know that it cannot handle an incoming large packet correctly. The implications of this is that fact alone is proof that it cannot handle QoS 1 and 2, because QoS 1 and 2 and the 311 protocol require that you keep a copy of the message in case it needs to be resent. You cannot keep a copy of that message if you've never had a copy of that message, because every time a fragment of it came in, every time you got 1K, you sent it to the user and go, oh, that's your problem, mate. You've got to deal with that. And that abdication of responsibility, I know this really shouldn't happen because we're talking about facts. That annoys me. That is the laziest and most rubbish piece of code I think I've probably ever seen. So I'm going to take a deep breath and get back to the facts. That is the absolute fundamental requirement of the library to do. Not only because that's what the library should do, but because if it doesn't, it cannot implement QoS 1 and 2 because it cannot hold the full packet which it needs to hold. And the worst thing is, if you then allow and expect the user to do it, it's a non-trivial task. The likelihood is that if he does it wrongly, your program's going to crash. So this is unforgivable, and if it had been done by anybody that ever worked for me in my past career, they would instantly be fired. What also goes against it being able to do QoS 1 and 2 is that it contains no code to operate QoS 1 and 2 recovery. I'm sure that the author doesn't even know what that means. Yet he still claims that it does it, which starts to border on deceptive. But even if it did have that code in there, and or any code for session management, which is again an absolute requirement of QoS 1 and 2 and part of the protocol, and which it has no code whatsoever to deal with, even if it had all those things, it still couldn't do it because it doesn't reassemble the incoming packet. Now at this point, I'm hoping that you realise that even continuing to think about using this library is a pretty poor decision. However, I shall continue with a brief summary of what we've learnt so far about this problem. That the code has no knowledge of the buffer size, it has no control over the transmit rate, it has no control over the receive rate, it has no control over the receive size, which it delegates to the user, but it provides a faulty API for a number of other reasons we won't go into now, which prevent that packet from being reassembled correctly. So, as long as the packets are always smaller than the minimum buffer size, by luck, it's not a problem, is it? As soon as you get one that is, that's it, you're gone. You've got no hope whatsoever of handling it correctly. And there is no flow control, which in itself is an issue, but there's no mitigation of the overlap bug. So all in all, perfect storm. It's absolutely guaranteed that this library does not and cannot work, and only appears to do so by accident. So now you understand all that and the mechanism behind, you look at the problems that come up again, they're no longer surprising, are they? Random disconnection and crashes, we know why, because anything can happen. We know about the problem with large packets. We know why it can't handle the rapid publish because of that overlap bug. We know why it behaves or crashes differently depending on the build options, because the build options determine the size of the buffers that are allocated, and if you don't know how big they are, if there's twice as many, it's going to take twice as long for the problem to occur. Whatever. I personally documented 16 fatal bugs in relation to all of the above. Now, just for comparison, Pangolin, the library I wrote, it mitigates the overlap bug by 1, finding it, fixing it, and then creating my own copy of the patch library and using proper flow control. So I keep a queue of everything that I sent, every ACK with the size that it sent, and as every TX rather, and as the ACKs come back in, I pair them up, match them off, take them out of queue, and so there's never any unexpected flows. So I can overlap. I can send 10 transmits in a row. They go in the queue. As the ACKs come back in, I knock them out one at a time. Now the ACKs do come back in because I fixed the library. So those two things together sort out 90% of the problems. Sorry, 10% of the problems. 90% of the problems are sorted. Oh no, yeah. That fixes the dangling pointer problem as well. It also dynamically calculates the LWIT buffers, and then it limits the size of a transmit that it will accept. It tells the user, that's too big, sorry, bye-bye. What it will do is it will take anything up to a half of the free heap, and the reason it's half is because it has to, at the point which it sends it, there's 2 copies in memory, so it can only be half as big as the maximum free memory. And it will fragment any sized packet up to that size into the proper buffer sized slices, put them in that properly controlled ACK queue, and then properly unack them when they come back. It does the same on receiving a large packet. So as it comes back in, once it looks like it's going to get past the half of the free heap, it cancels the packet and then just rejects every incoming packet until it's sent, and then sends, causes an error saying, there was a missed packet coming. If it's less than that free heap, it assembles the packet correctly and sends the entire packet to the user code. It then keeps a copy of it. That's why it's after. And if there is then a QoS 1 or 2 problem, it's got that packet to retransmit, so it can correctly follow MQTT 3.1 1 and QoS 1 and 2. If you're really interested to know how it does it, that's how it does it. It's quite a complex piece of code. Just for comparison, so that we can finish now, this library is kind of that part of it, but only at QoS 0, only with small packets, and only at a slow rate. But it just gives you an idea of how much this library does not do that it must do to be able to even get close to making the claims that it makes on its opening page. So back to that opening page, let's update it. Change it for Pangolin. That's still the same. I can't change that. So all of those things that this library claims, which are incorrect, Pangolin does correctly. It adds large packet handling, it's faster, and it doesn't randomly crash all the time. It's not available in the platform IO registry, but as I've said before, that's a matter of the greatest difference to me, and I don't give a flying hoot whether it is or it isn't. It's there. If you want to use it, use it. If you don't, don't. But now that you have all the facts about what is wrong with Pangolin, what is wrong with asynMqttClient, you can make an informed decision. Now in the next video, because this one is already 40 minutes long and that's way too long, in the next video we can look at the evidence. And really, you're only going to want to do that if you still have any doubts about what you've seen so far. If you do, I question your judgment. However, I accept the fact that bold claims require bold evidence. I have it all. It'll be in part 2, and I'll see you then. As always, thanks for watching. Please remember to subscribe, like, click the notification button and support me on Patreon if you can. Thanks, and see you next time.